particular case, there's an activation energy for the forward reaction of 132 kilojoules per mole. And there's an activation energy for the reverse reaction of 358 kilojoules per mole. And there's also a delta E for the reaction, which is this line from reactants to products, which in this case is minus 226 kilojoules per mole. So do you think this reaction is endothermic or exothermic? What do you think, exothermic or endothermic? It's exothermic. And if you look back in your notes, you talked a little bit about the relationship between delta H and delta E. And and they're actually pretty similar. Delta H usually equals delta E plus a change in PV. So for gases, it's about 1 or 2% difference, and for solids, there's really negligible difference between delta E and delta H. So they're pretty similar types of values. So we can think about what delta E really is, and so delta E in terms of activation energy is going to be equal to the activation energy for the forward reaction minus the activation energy for the reverse reaction. And in this particular case, we have 226 kilojoules per mole is our delta E. And for our forward reaction, we have 132 kilojoules per mole. And for the reverse reaction, the activation energy for the reverse reaction is 358 kilojoules per mole. And so these should all equal up to each other. And so if you know two of these values, you can calculate the third. And this is one of the equations that you have to memorize for the final, because it's a sort of a conceptual thing that you need to understand what this diagram says, that this plus that is equal to that these all add up to each other. And if you have a negative value here, that means it's an exothermic reaction. So this delta E is a change in internal energy of the system, and you can determine that value experimentally, say with a calorimetry experiment. Okay, so let's keep this in mind and go on and take a look at how this connects back with some other things that we have already talked about in this course. So for an elementary reaction, and I think for all of us, there's always some activation energy barrier to overcome. There's always some positive activation energy to overcome. And because there's always this activation energy to overcome, increasing the temperature is always going to increase the rate of an elementary reaction. It's always going to make it easier to get over that activation energy barrier. But for an overall reaction, increasing the temperature may not increase the rate of the reaction. So let's consider why that would be true.